Good day everyone. My name is Indanagi daughter of Ravichandran. My METI number is P122410511. Today I'm here with my teammates to present our assignment for Bert 133 Advanced Electrical Circuit. Our assignment title is Transfer Function and Board Plot. To start, let's define the transfer function. A transfer function is a mathematical expression that shows the relationship between the input and output of a linear time invariant system in the frequency domain. It plays an important role in a circuit analysis and control system, allowing engineers to predict how a circuit will behave at different frequencies. It can be present as the ratio of output voltage to input voltage or output current to input current depending on the system. Now I will explain part 8 transfer function. This is the equation that we got, which is h omega equal to 50 j omega divided by j omega plus 4 j omega plus 10 power of 2. The first step we do is we factorize the equation. After we factorize the equation, we get this equation, which is h omega equal to 50 j omega divided by 400 bracket j omega over 4 plus 1 bracket j omega over 10 plus 1 power of 2. After we factorize the equation to identify the frequency dependent elements, the next step we do is we simplify the equation by multiplying out the denominator and combining the constant. This is the denominator and this is the answer after we simplify it in constant form. So the final answer we get is h omega equal to 0.125 times by j omega over j omega over 4 plus 1 bracket j omega over 10 plus 1 power of 2. Now we move on to the magnitude both plot. Using the transfer function, we substitute the values into both formula and apply logarithm roots to simplify. By using the above equation, we need to substitute the value into the formula below. From the formula and table above, we can obtain the final equation for magnitude both plot.
Hi, my name is Nurani Aya Binimo Abasdi. I will explaining the magnitude both plot for a given transfer function. Starting at 20 log omega, the plot initially raises with a slope of positive 20 dB per second per decade. This is because the zero at the origin, which is increased the gain as the frequency increases. At omega 4, we encounter the first spoke. This causes the slope to decrease by 20 dB per decade, flattening the curve. Now the slope becomes 0 dB per decade, which means the gain stay constant for a short range of frequencies. Then, at the omega 10, we hit a double pulse, which each pole contributes at negative 20 dB per decade. Drop the double pole result in negative 40 per decade. Slope after this point, the gain drop off quickly as the frequency continue to increases. As also the constant in the transfer function, which is 0.125, shift the entire magnitude plot downward by about negative 18 dB per second, 18 dB calculated using 20 log 10 0.125. By looking at the book plot, we can clearly see where each pole and zero effect by the slope, making it easier to understand the frequency behavior of the system. We can also use this kind of plot to estimate or reconstruct the transfer function by identifying these changes in slope and matching them in standard board plot patterns.
Hi and Assalamualaikum. My name is Nur Amira Besara binti Marzanan. Today I will explain how I get for question about Facebook load. The question is H omega equals to 0.125 times 2 j omega over j omega over 4 plus 1 times 2 j omega over 10 plus 1 square. So the first step is by using the above equation, substitute the value in the formula below, which is theta equals to tangent negative 1 omega over z. For this question, as you can see, h omega equals to 0.125 times 2 j omega over 4 plus 1 times 2 j omega over 10 plus 1 square. In the yellow box is how I simplified it. So j omega plus 4 equals to 4, 1 plus j omega over 4. and then j omega plus 10 equals to 10 j omega over 10 square. J omega plus 10 equals to 10 1 plus j omega over 10 square, and then j omega plus 10 square equals to 10 1 plus j omega over 10 square equals to 10 square 1 plus j omega over 10 square. And then I use in the yellow box into the next equation is h omega equals to 50 j omega over 4 1 plus j omega over 4 times to 10 square 1 plus j omega over 10 square. That I already find it. And then the next is h omega equals to 50 j omega over 4 times to 100 1 plus j omega over 4 times to 1 plus j omega over 10 square. And then the next is h omega equals to 50 j omega over 400 because 4 times 100 is 400, and then 1 plus j omega over 4 times to 1 plus j omega over 10 square. And then how we get 50? Because 0.125 times to 400 we get 50, or if you want to confirm it, we can 50 divide by 400 and then we will get 0.125, so it's the same thing. And then we continue to h omega equals to 50 over 400 times to j omega over 1 plus j omega over 4 times to 1 plus j omega over 10 square, and then the final answer is h omega equals 1 over 8 times to j omega over 1 plus j omega over times to 1 plus j omega over 10 square. And our magnitude board plot HDB equals to negative 18.06 plus 20 log modulus omega minus 20 log 1 plus j omega plus j omega over 4 minus 40 log 1 plus j omega over 10. And our Facebook plot is j omega equals to 90 degrees. And why must 90 degrees? Because j is imaginary. So j equals to square root of negative 1. So j omega equals to 0 plus j omega. Because this is imaginary and then this is the real. So that's why we get j omega equals to 90 degrees. We continue it to 1 plus j omega over 4 equals to negative tangent negative 1 omega over 4. And then 1 plus j omega over 10 square equals to negative 2 tangent negative 1 omega over 10. And why must negative tangent? Because in a board plot, when term at the below denominator, the face will be minus. And where is our denominator? Our denominator is 4 and 10. And our term is omega. That's why we get negative tangent. And then we also get negative 2 tangent for denominator 10. And we continue to h omega equals to 0 degrees plus 90 degrees minus tangent negative 1 omega over 4 minus 2 tangent negative 1 omega over 10, and 1 minus 0 degrees because at the previous we get 50 j omega, and 50 is a real number. That's why any kind of real number turns to 0 degrees. So 0 degrees plus 90 degrees, we get 90 degrees. So the final answer is theta equals to 90 degrees minus tangent negative 1 omega over 4 minus 2 tangent negative 1 omega over 10. For graph explanation, as you can see in this graph is board plot graph, which is we can see that for phase starter at positive 90 degrees because we have j omega. In the formula, j omega equals to positive 90 degrees, negative j omega equals to negative 90 degrees, and 1 equals to 0 degrees. Why? Because 1 is a real number. Same to previous calculation, which is 50 j omega. 50 is a real number, that's why it turns to 0 degrees. So when the frequency is higher, so the phase will slowly drop near to omega over 4. Omega equals 4, and then will drop faster when near to omega equals 10. Finally, the phase will near to negative 180 degrees. So this system shows that the highest frequency, the system will become more slow. That's all from me. Thank you.
Now we will move to zero and poles part. Okay, this is our final equation, which is h omega equal to 0.125 times by j omega divided by bracket j omega over 4 plus 1 bracket j omega over 10 plus 1 power of 2. From this equation, we can identify that j omega is 0 pole, j omega over 4 plus 1 is simple pole, j omega over 10 plus 1 power of 2 is double pole.
Hello and welcome everyone. My name is Neela of Kumarasamy. Now in this video I will present to you the Bot plot to transform function conversion. As you can see from the Bot plot graph of E, the magnitude response starts off with 20 dB per decade slopes, then it becomes constant at 20 dB and finally it decreases with a slope of negative 40 dB per decade. The 20 dB per decade slopes begin at omega is equal to 5 radius per second, indicates the presence of a zero at 5 radius per second. The flat region starting after omega is equal to 10 radius per second shows that a pole at 10 radius per second. The steep decline of negative 40 dB per decade after omega is equal to 100 radius per second implies the presence of two poles at 100 radius per second. As you can see the graph, the omega value is 5, 10, and 100, and the k value is 10. Now let's move on to the calculation part. As in our previous slide, we have find the value for 0 slopes, pole slopes, and 2 poles. We can directly substitute the value in this equation. To simplify this expression, we multiply each term by constant to eliminate the denominator inside the bracket. First, we rewrite the equation. Now we multiply out the constant and cancel the same common denominator. After that, it becomes simplified frequency domain transfer function. After that, we replace the j omega with s to get the Laplace transform, and that completes the conversion from the Bot plot to the transfer function. Thank you so much.
In part A, firstly, we need to identify the poles and zeros. But for poles and zero, it must be in terms of tables given in part A. In that tables, it is a requirement to the poles and zero. We factorize and simplify the equation until we get the similar equation as in the tables. Magnitude Bot plots reflect on the zero origin, a single poles at omega 4 and double poles at omega 10. When the plot rises at a rate of 20 dB per decade, due to the zero, it increases again with frequency. At omega 4, it shows as a simple pole causes by the slope to level off that reduced rate to 0 dB per decade. While at omega 10 show that as a double pulse at that changes that slope to negative 40 dB per decade that rapidly decrease in gain. The constant of 0.125 in the transfer function at a vertical offset of the about negative 18 dB per across the entire plot. The slope in this graph clearly show that how each pole and zero affect the frequency response. The phase Bot plot of the transfer function or h omega is accurately represented in the graph provided. Initially, the plot begins at positive 90 degree, which come from the j omega term in the numerator that contribute a constant positive 90 degree phase shift. As the frequency increases, the curve starts to decrease near omega 4, corresponding to the first order pole. This introduces the phase lag of clearly marked on the graph by a gentle downward slope. A second steeper decline begin near omega 10 caused by the double pole, contributing a lag of this combined. The effect causes the phase to continue decreasing, leveling off at negative 180 degree, which matches the theoretically expression degree h omega equals to 90 degree. The graph visually illustrates these three key region and initially flat section at 90 degree and gradually drop at omega 4 and a sharper drop near omega 10 confirm the expected phase behavior of this system. In a nutshell, we are able to convert the transfer function to Bot plot by finding the magnitude and phase. Other than that, we are able to convert the Bot plots into transfer function equation by pointing out the equation by referring to the table. In magnitude Bot plot, we are able to understand that the gains respond to different frequencies, increase or decrease, depend on the location of the poles and zeros. By the changes of slope, we also can identify the important characteristic of the transfer functions. The phase Bot plot show how the phase angles of the system changes with frequency. It helps us understand how poles and zero affect the signal phases. In this case, the plot started at positive 90 degree due to the j omega terms. Then decrease as the frequency increases because the phase lag introduced by the poles. The first poles reduce the phase rate gradually, while the second order poles cause the sharp drop eventually reaching negative 180 degree. This shows how the higher or the poles have a stronger impact on the phase shift.